Okay, so this is Compton effect part 2, and so we're just going to take a look here at what is the wavelength of a 660 kilo electron volt photon, and what type of photon would this be? So because this is a photon, the energy is equal to Pc, right? And we want to find the wavelength. We've been given the energy, and so here the key is within the momentum. We know that momentum is just equal to h over wavelength, so you can devise that with this formula, or that the wavelength is equal to hc over E. All right. Because we've been given the energy in electron volts, specifically kilo electron volts, we're going to use H, or Planck's constant, using the 4.14 times 10 to the negative 15. C, speed of light, is just 3 times 10 to the 8, all over 660,000 electron volts. And this winds up being 1.88 times 10 to the negative 12 meters. Right? And so if you're taking a look, this is going to be probably within the X-ray / gamma ray range, because it is much shorter than regular visible light. Right? Not just a little bit and bring us into the ultraviolet. The next one tells us to find the momentum of a 6.0 mega electron volt proton. Now, this is not a photon. We cannot assume that this is moving at the speed of light because it is not an electromagnetic wave. Okay, so first thing we're going to do is we're going to change this into joules, because finding momentum of objects here, it's a little bit easier to do it within joules. So we're going to take that 6 times 10 to the 6 electron volts multiplied by 1.6 times 10 to the negative 19 joules per electron volt. That's going to get us 9.6 times 10 to the negative 13 joules. That is the energy of this proton. And so we're going to now find the velocity of this proton, because all this energy is equal to is 1/2 mv squared, or 1/2 times 1.67 times 10 to the negative 27. That's the mass of the proton. We're looking for v squared. So multiplying both sides by 2, dividing both sides by 1.67, and square rooting, right? So the manipulation looks something like this, right? 2e over m square rooted is equal to v. That velocity, using the numbers that we got, is going to be 3.39 times 10 to the 7 meters per second. Lastly, because we are looking for momentum, we're going to now multiply it again by the mass. So we're just using this velocity and this mass, and when you multiply those two together, you're going to get 5.66 times 10 to the negative 20 kilogram meters per second. Okay, I want you to try this again, but we're looking for the wavelength of this X-ray X-ray photon. So looking for the wavelength. Give this one a try. Pause the video and and we'll come back to you. Welcome back, and just like we did in example number 4, the energy is equal to the momentum times the speed of light. Because this is a photon, we can use this equation. We could not use it with the previous equation because it was not a photon. So manipulation, find the wavelength is equal to hc over E. Plugging in the numbers, because the energy has been given in electron volts, we're going to use Planck's constant as 4.14 times 10 to the negative 15 electron volt seconds, and you find that the wavelength is 1.24 times 10 to the negative 11 meters. So the next question we're going to take a look at here is a different manipulation that relates to the Compton effect. Okay, so in this scenario here, we're looking at the deviation of the photon as it hits an electron. So the photon is coming in here, hits the electron, and now it's going to scatter off. This angle of deviation is 60 degrees, and because it is transferring some of the energy to here, it is going to be getting longer in wavelength and losing some of its energy. The question is, what is the change in the wavelength here? Now, this neat little equation is on your formula sheet, which is h over mc 1 minus cos theta. Now, if you're looking at this, you may say, okay, well, mass of a photon, what's happening there? Well, this is actually the mass of the object that it is colliding with, and in this case it is colliding with an electron. And so it's just a little bit here. This formula does not come up very often on the exams, but I thought I'd better run through at least one example with you. We really have all the numbers here. So if we take a look here, the change in the wavelength is equal to h. We're going to use 6.63 times 10 to the negative 34 joule seconds. The reason why we're going to use this one is because we've got other standard units that we're using, such as 9.11 times 10 to the negative 31 kilograms, which is the mass of that electron. The 3 times 10 to the 8, which is the speed of your photon, 1 minus cos 60 degrees. Now, as you type all this in, you're going to find that the change in the wavelength will be approximately 2.05 times 10 to the negative 12 meters. Okay? And that is what the question is asking for, the change in the wavelength. So this going 5.00 times 10 to the negative 11, it's going to have a change of 2.05 times 10 to the negative 12. Because it's transferring some of its energy to this electron, as it collides and bounces off, this particular wavelength here is going to be 5.02. No, sorry, not 5.02, 5.2. Lost my decimal places. 5.2 times 10 to the negative 11 meters in terms of its length. Which leads us to the last question. What is the speed of the electron after the collision? Well, in this case here, first thing we're going to do is we're going to take a look at what's happening with the change in momentum of the electron, because really the change in momentum is going to be equal to the mass times the change in velocity of the electron, law of conservation of momentum. And so we're going to take a look at the momentum here of the electron. before h over wavelength, and so the momentum we'll use we will use 6.63 because we want our momentum in kilogram meters per second or Newton seconds. 6.63 times 10 to the negative 34 divided by the wavelength of 5 times 10 to the negative 11. This is the momentum that we have before the collision of the photon. The momentum after, well, afterwards, this photon had lengthened, and so 5.2 times 10 to the negative 11, because we're adding the change to the original wavelength. So taking a look here, this is now 1.321 times 10 to the negative 23. And so we see that we have lost a little bit of momentum. That change in momentum overall of the photon is 0.005 times 10 to the negative 23, or 5 times 10 to the negative 26 kilogram meters per second as the standard units. And so that momentum is being transferred to the electron. So we're just going to do this change in momentum. This 5 times 10 to the negative 26 is equal to the mass of the electron times delta V. So the electron being 9.11 times 10 to the negative 31, change in velocity. Dividing both sides by that mass, you will find that this is now moving at 5.5 times 10 to the 4 kilogram, not kilogram meters per second, just meters per second, as its change in velocity. But because this electron was at rest before, that does wind up being its final velocity, 5.5 times 10 to the 4 meters per second. Okay, thanks for watching. If you got any questions, let me know.